Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element plutonium. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Plutonium is the 94th element in the periodic table. Its atomic number is 94 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Dmitri Mendeleev, often considered one of the fathers of the modern periodic table, was trying to make sense of how the elements related to each other. He was smart enough to know he didn't know everything, and there was room for future discoveries. His table was originally published in 1869, and you can see he future-proofed his table by leaving spaces for as-yet undiscovered elements. In our case, he left a space for plutonium after the also as-yet undiscovered neptunium in his table. We don't have to go back to ancient times for the discovery of plutonium, only back to the Manhattan Project during World War II. These UC Berkeley physicists, Edwin McMillan, Glenn Seaborg, Joseph Kennedy, and Arthur Wall, discovered that irradiating uranium-238 with neutrons produced a new element. Note the photos of Kennedy and Wall are from their Manhattan Project ID badges. Although this discovery happened in 1940 and 1941, because of the sensitive nature of work with fissile materials, they had to wait until after World War II ended to actually publish their findings. Both McMillan and Seaborg received a Nobel Prize for their work. They used the new 60-inch cyclotron built by Ernest Lawrence at the UC Berkeley Radiation Lab, later called the Lawrence Radiation Lab, and even later the Lawrence Berkeley National Lab after the word radiation became too politically sensitive for Berkeley. Using the accelerator, they smashed deuterons into uranium nuclei to make plutonium. Let's look at that process. By the way, that's Ed McMillan on the right. They started with uranium-238 atoms. This is the most common isotope of uranium and is not fissile. I'll show just the nucleus, since that's all that really matters. A deuteron is a nucleus of deuterium, a heavy isotope of hydrogen with one proton and one neutron. This charged particle was accelerated and smashed into the uranium-238 nucleus, resulting in a nucleus of neptunium-238 and a couple free neutrons. Let's let them continue on their way. Neptunium-238 has a half-life of 2.355 days, so the physicists didn't have to wait long before it decayed by beta particle emission to become the desired plutonium, in this case, plutonium-239. This was the first sample of plutonium produced at the Rad Lab in which nuclear fission was detected. The sample was deposited on the small gray disk here held in place with a paperclip inside the cigar box. The sample was eventually gifted from Glenn Seaborg and Emilio Segre to the National Museum of American History. They named their new element after the 9th planet from the Sun, Pluto, named for the Greek and Roman god of the underworld. Hence, the name of the element was plutonium. This was the third element in a row named after the outer planets. In order from the Sun, we have Uranus, contributing its name to uranium, element 92, Neptune, used to name neptunium, element 93, and Pluto, lending its name for this program's element, plutonium, element 94. These planet images are not to the same scale. While Uranus and Neptune are about the same size, the planet Pluto is much, much smaller. Yes, I still consider Pluto a planet in spite of Neil deGrasse Tyson's opinion on planetary membership. No need to comment. Plutonium is a member of the actinide series of elements down at the bottom of the table. It's the sixth element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides and their isotopes are radioactive. Let's look at isotopes. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 94 protons for plutonium. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 22 known isotopes of plutonium, and as I mentioned in the previous slide, we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of plutonium are radioactive. We find plutonium in nature only in trace amounts, resulting from neutron capture by uranium. More on that later. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place. You've used a topographic map, I assume. All these various isotopes of plutonium occupy the same place in the periodic table. Of the isotopes of plutonium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest plutonium half-life is plutonium-244, with a half-life of 81.3 million years. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we started with 1,024 atoms of any radioactive isotope. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait 1/2 life, 1/2 of your isotope will decay, and we'll have 512 atoms left. If we wait 1 more half-life, half of that half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice that there's 1 remaining atom after 10 half-lives. If we waited 1 more half-life, our remaining atom would have a 50-50 chance of decaying in that time. All radioactive elements decay and transmute into other daughter elements, something the ancient alchemists dreamed about but didn't know was happening around them all the time. Although I'm simplifying this a bit, atoms can decay by alpha or beta decay. I want to show you the decay series of plutonium, and I want to do it on a chart you'll see in many physics texts and which I'll attempt to show you in the next slide. First, let's look at what alpha and beta decay look like on the chart. We're only using a very small portion of a much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us what element we're dealing with, each row is one unique element. As I mentioned, when an isotope decays, it can do this by emitting an alpha particle or a beta particle. An alpha particle is made up of 2 protons and 2 neutrons, 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium isotopes have 88 protons. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, and that electron is spit out of the nucleus as a beta particle. This means the nucleus gains a proton, but does not change its atomic weight significantly since electrons are so light. This time, we'll start with thorium-234. Gaining a proton, but not changing its atomic weight, moves us up 1 row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Let's take a peek at the whole chart. Here's the portion of the chart of nuclides that contains a row for plutonium. But let's back away to see the whole chart. Here you see all the stable and radioactive isotopes we know or speculate about, from hydrogen down in the lower left, through the as yet undiscovered row for element 119, temporarily named ununium. This chart is a bit different from the one I'm using in that the horizontal axis here is the number of neutrons in the nucleus, not the total number of neutrons and protons, but the idea is the same. My charting method makes it easy for us to see the alpha and beta decays, but back to our decay series. Now let's take a look at the plutonium-239 decay chain. It's actually the same as the uranium-235 decay chain we saw in a previous edition of Tales from the Periodic Table because plutonium-239 decays into uranium-235, but let's do it anyway. As I mentioned, our starting point is plutonium-239. This decay series is often called the actinium series, but let's stick with the plutonium title to reduce confusion. I'll list the isotope, decay mode, and half-life at the top for your reference. Plutonium-239 has a half-life of 24,110 years. It decays by alpha into uranium-235. This also decays by alpha into thorium-231. Thorium-231 decays by beta, remember we move up 1 square for betas, into protactinium-231. That decays by alpha into actinium-227, the longest-lived actinium isotope. The actinium-227 can decay in 2 ways. 98.62% of the time, it decays by beta to thorium-227, a different isotope of thorium than we saw before. But 1.38% of the time, the actinium decays by alpha into francium-223. The francium-223 decays by beta to radium-223. But our thorium-227 from before decays by alpha to radium-223 as well, giving us 2 paths to this element. Radium-223 decays by alpha to radon-219, which decays by alpha to polonium-215, which decays by alpha to lead-211, a radioactive isotope of lead, which decays by beta to bismuth-211, which decays by alpha to thallium-207, which finally decays by beta to lead-207, which is non-radioactive and stable. That was a roller coaster ride. There are other decay chains. See the previous episodes for those. Since we're on our 11th radioactive element, 12th if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity, the rate particles are emitted. This is probably the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second, but you need to take into account the size or area of the detector and its distance from the source and multiply the measured counts per second as if your detector could completely surround the source to catch all the disintegrations in every direction. The international unit for this is the becquerel, named after Henri Becquerel, who discovered radioactivity. 1 becquerel equals 1 disintegration per second, so most sources are in the kilo, mega, or even giga becquerel range. In the US, we also use an older unit, the Curie, obviously named after our dynamic duo, Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium. Radium was discovered by the Curies. Get it? 1 Curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Radiation carries energy, and that energy is deposited in your body or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is about the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A Gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milli or micrograys or something like that. In the US, we have used the unit of the rad, or radiation absorbed dose, which is 1/100th as large as the Gray, but still a large amount of radiation. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the REM, which stands for Radiation Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are human health-related units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem, per year in the workplace. You normally absorb about 67 millirem every year from the environment around you. That's 1/75th of the allowed annual dose. A dental X-ray exposes you to about 1/2 of a millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem, and a chest CT scan gives you up to an 800 millirem dose. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits always outweigh the risk. I normally talk about the abundances of elements on this slide, but because of the relatively short-lived radioactive nature of plutonium, at least compared to the age of the universe, there's not much to say here. There's really none to speak of in the universe, having all decayed away by now, and none in the sun. Likewise, none in meteorites, and not enough naturally in the Earth to talk about except the tiny amount, maybe 9 grams, probably left over from the formation of the Earth. It's absent in the oceans, and thankfully, of course, none in us. That was a lot of red X's. Even though there's only 9 grams of natural plutonium on Earth, there's a lot more artificially produced plutonium. An estimate places the total amount of plutonium at around 565 metric tons. Of this, 140 tons are in weapons or readily available for weapons. That 565 tons would be a cube almost 305 centimeters, 10 feet on a side, about twice as tall as a human. Incidentally, this is way more than the critical mass for plutonium. Our cube would cause a massive chain reaction. Plutonium has a density of 19.816 grams per cubic centimeter. That's a really dense element. As a reminder, the density of water is only 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds. You can see plutonium's density is slightly more than gold. Here's a graph of the elements from highest density to lowest density. I have a set of blocks, so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, plutonium's density is 19.816 grams per cubic centimeter, near the top of the chart, the 6th densest element. I'd be arrested for owning a cube of this stuff. Plutonium has a fairly low melting temperature of only 640 degrees Celsius, 1,184 degrees Fahrenheit. That's the 67th highest melting point. Below the middle of our chart, slightly above lead or zinc, but slightly less than aluminum or magnesium. Plutonium boils at a very hot 3,230 degrees Celsius, 5,846 degrees Fahrenheit, giving it the 28th highest boiling point of all the elements. That's about 2,590 degrees Celsius above its melting point, giving it a large liquid temperature range. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range. Plutonium is not far behind, with a 2,590 degrees Celsius range, the 5th largest liquid temperature range of all the elements. The smallest liquid temperature range belongs to neon, which is liquid in only a 2.51 degrees Celsius range. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. If we compare the size of the plutonium atom to that of hydrogen, we'd see something like this, though I'm just estimating the atomic diameter by using its covalent radius, since it really hasn't been measured accurately yet. Plutonium is about 4.4 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are perplexingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium, at the top left, to the smallest, helium, at the bottom right. My estimated size of plutonium places it in the upper region of the chart, around the size of many of the rare earth lanthanides, and specifically holmium and terbium, around the 11th largest atom. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of plutonium. It has a fairly complex spectrum with a wide selection of colors spanning the spectrum from red to violet. Spectra of the elements uniquely identifies them to scientists, as each gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Plutonium has three main uses: powering nuclear reactors, powering and heating spacecraft, and as the fissile material in atomic weapons. So, mostly good stuff, but horrifyingly terrible on the bad side. Let's first talk about applications that do not require critical masses of plutonium. Here, we see a disk of highly purified plutonium-239 being held in a glove box. Since plutonium decays by alpha, the glove box is sufficient to protect the fellow holding the large amount of plutonium, though I'll bet the disk is warm to the touch. This is a pellet of plutonium-238, not the stuff in an atomic bomb, which is plutonium-239. The pellet is not red hot because it was just taken out of an oven. It's red hot because it's so radioactive, the alpha particle emission heats it to this temperature. This heat can be used to generate electricity in what's called a radioisotope thermoelectric generator, or RTG. NASA's version of this is called the Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG. Here's the power generator waiting to be installed in the Mars Perseverance rover. We'll look at the inside of the MMRTG shortly. Plutonium is heavily used in deep space and planetary missions by NASA. The New Horizons spacecraft, which recently visited the planet Pluto, had one of these nuclear generators on board. You can't use solar panels that far out. The Sun, almost 4 billion miles distant, looks like a very bright star in Pluto's sky. There's not enough light energy to generate the needed electricity. New Horizons MMRTG supplied about 245 watts of power at launch. As the spacecraft continued on its mission, the plutonium decays, supplying exponentially less and less power until the late 2030s. The generated electricity won't be enough to power or heat the spacecraft. MMRTGs were also used in the Pioneer and Voyager spacecraft, which have now left the solar system and are sailing through interstellar space. MMRTGs are also used on the Mars rovers, Curiosity, seen here, and Perseverance. With both rovers' large power budget, solar panels won't do the job. It takes a lot of energy to do all that moving around. You need a small nuclear-powered generator, here, mounted on the rear of the rover. Curiosity's generator produced about 110 watts of power at the beginning of the mission. Here's a great NASA animation of what's inside an MMRTG. The outside layer of the cylinder consists of many thermocouples that turn heat into electricity. Heat is generated by plutonium oxide inside a general-purpose heat source, or GPHS. The rectangular GPHS contains 2 cylinders, each of which contain 2 pellets of plutonium-238 oxide, glowing red hot at launch. These plutonium pellets are welded into strong iridium cylinders and then inserted into graphite impact shells to contain the plutonium in case of spacecraft malfunction at launch. 2 graphite impact shells are assembled into a general-purpose heat source, and 8 of these are stacked into an MMRTG. Again, the heat from the plutonium generates electricity used to power the spacecraft. Excess heat is used to keep critical spacecraft components at working temperatures, or, if not needed, radiated away by the fins into space. Find out more here. Let's look at some real photos of the internals of the MMRTG. Here's a better photo of the plutonium-238 oxide pellets before they're encased in a protective cylinder called the graphite impact shell. Again, these are glowing red hot only from the intense alpha particle radiation given off by the plutonium. Here's the cylindrical graphite impact shell, which also heats up to red-hot temperatures. Two of those are inserted into the rectangular block called a general-purpose heat source. The purpose of all this is to keep the plutonium from escaping in the unlikely event the spacecraft fails during or right after launch and the MMRTG falls back to Earth. There's a very good chance that these precautions will prevent the spread of any radioactive material. To make plutonium-238 used in the MMRTG, you scavenge and purify neptunium-237 from spent nuclear fuel pellets like the one you see here. Neptunium-237 is long-lived with a half-life over 2 million years. This means it's a problem because you have to store nuclear waste for many half-lives. Making plutonium-238 with this process solves the storage problem by getting rid of the long-lived neptunium and substituting it with the much shorter-lived plutonium. Let's see how. You put the neptunium-237 back in a reactor where excess neutrons are available. When one of those neutrons is absorbed by the neptunium-237, it becomes a new isotope, neptunium-238. Now, neptunium-238 has a much shorter half-life than its parent, only 2.117 days. It decays by beta to become plutonium-238, which has a half-life of only 87.7 years. Still long, but much better. Storing this shorter-lived isotope is a smaller problem. But we aren't going to store it, as I've shown. We'll use it. Plutonium-238 is very useful and in short supply. The U.S. used up its stockpile of plutonium-238 in 1988 and has been purchasing more from Russia. Even Russia stopped shipping us plutonium-238 in 2010. That being problematic, the U.S. has started up a program to produce plutonium-238 once again. By this year, 2025, the Department of Energy plans to produce 1.5 kilograms or 3.3 pounds of plutonium-238 dioxide per year. There's 4.8 kilograms or 10.6 pounds of plutonium in each MMRTG, so it takes a bit over 3 years to make enough plutonium for one spacecraft. Spacecraft aren't the only devices that have been powered by plutonium. Using the same technology, some thought it would be a really cool idea to make cardiac pacemakers with plutonium-based batteries. I can somewhat see their point. You'd have a pacemaker that would last a long time. It was expected they would last a minimum of 15 years, and some lasted over 30 years, often outlasting the patient. More than one company made these. When removed, the surgeons, or morticians, are supposed to contact the Off-Site Source Recovery Program at Los Alamos National Lab. Their mission is to remove excess, unwanted, or disused U.S.-origin radioactive sealed sources, including atomic pacemakers. If my calculations are correct, these pacemakers contained plus or minus 200 milligrams, 1/5 of a gram, of plutonium-238. A typical U.S. penny weighs 2.5 grams, or 12.5 times as much. Let's get back to the basic fission process. Fission of plutonium happens when it's hit by a stray neutron. The extra neutron destabilizes the nucleus, which then splits into two smaller, lighter nuclei. The split, or fission of the atom, releases energy and several additional neutrons. Those neutrons are now free to cause more plutonium atoms to fission. Since many neutrons are released by a single fissioning atom, and each neutron can cause a further plutonium atom to fission, the number of fissioning atoms can grow exponentially in a chain reaction. Here's an example of a chain reaction. The box has a large number of unsprung mousetraps with ping-pong balls on them. A single ping-pong ball starts the reaction, which builds exponentially until we eventually run out of loaded traps, a sort of nuclear explosion of ping-pong balls. This is similar to our plutonium atoms all waiting to be hit by a neutron and then fission. Like the ping-pong balls, an exponentially growing number of splitting atoms is called a chain reaction. We've used plutonium-239 as an example, but other isotopes of uranium and plutonium, among others, also have this quality. Those extra neutrons and their ability to create a chain reaction means uranium and plutonium are useful in nuclear reactors if you can control the number of atoms fissioning, but in an uncontrolled chain reaction becomes a nuclear bomb. Uranium and plutonium's ability to participate and cause this chain reaction is because they're what's called a fissile material. Let's return for a moment to those reactors. Most reactors use uranium as their main nuclear fuel. As this fuel is used, some of the uranium captures neutrons, becoming plutonium-239. We'll see this process in the next slide. Since plutonium is also fissile, it could be used in reactors combined with the more traditional uranium in what's called MOX, or mixed oxide fuel. The uranium and plutonium fuel pellets are actually oxides, not the metals. Reactors must be specially designed to use this fuel, and a few outside the United States are now licensed to do this. One useful aspect of this type of reactor is that it can use plutonium-239 from surplus nuclear weapons and provide a way to reduce those stockpiles. Truly swords to plowshares. Here's what's going on inside uranium-fueled reactors that produces plutonium-239. You start with uranium-238, the most common isotope of uranium with the long half-life of 4.5 billion years, and it's also part of that low-enriched fuel of the reactor. Inside the reactor, there are lots of excess neutrons. If a uranium-238 nucleus is hit with a neutron, it transforms into uranium-239, which has a short half-life of only 23 minutes. This decays by beta particle emission into neptunium-239, which also has a short half-life of only 2.355 days. This also decays by beta and becomes plutonium-239 with a fairly long half-life of 24,110 years. You can almost ignore those intermediate isotopes since they decay away so quickly. Uranium-238 is changed into plutonium-239 in the reactor. You may have seen photos of nuclear reactors. The big towers with all the steam are not the reactors. They just provide cooling by turning water into steam. The reactors are usually in less spectacular buildings, specially designed to contain the fissile material should the reaction get out of hand, like it did at 3 Mile Island and Fukushima, and like it wasn't contained at Chernobyl. About 10% of the world's electricity comes from nuclear power. Plutonium plays some role in this power generation. The critical mass of plutonium is the smallest amount of plutonium needed to maintain a self-sustaining nuclear chain reaction. I'm going to use plutonium-239 as an example. The exact critical mass of plutonium depends on a few key factors. Its enrichment level. The more plutonium-239 in the sample, the less material is needed. For example, highly enriched plutonium has a critical mass of about 11 kilograms shaped in a bare sphere. Compare this to 52 kilograms for uranium-235. The shape makes a difference. A sphere is the most efficient shape for minimizing neutron loss and achieving criticality. Materials like beryllium or graphite placed around the plutonium can reflect otherwise escaping neutrons back into the core, reducing the critical mass significantly, sometimes by more than half. Higher density helps neutrons hit other atoms more easily because atoms are closer together, so compressing the material can also lower the critical mass. We'll talk more about that in a bit too. Understanding critical mass is essential in nuclear weapons design, where achieving supercritical mass is necessary for an explosion, and in design of nuclear power plants, where criticality is carefully controlled to avoid accidents. Speaking of accidents, experiments at Los Alamos did claim 2 lives. I bring up this tragic, albeit interesting story because I know I'll get comments if I don't. Both Louis Slotin and Harry Daghlian died due to overexposure to radiation in 2 separate incidents. Both experiments involved the same sphere of plutonium, which was, eventually, and appropriately, named the Demon Core. Both physicists were experimenting with criticality, how close you could bring the core to going critical without going over the edge. Richard Feynman called this tickling the tail of the sleeping dragon. Unfortunately, both physicists woke the dragon. Here you see both Daghlian and Slotin were present at the top of the shot tower assembling the Trinity test bomb. Their accidents occurred in experiments after the Trinity test, which we'll talk about in a bit. First, let me say these photos are from a recreation of both accidents. The sphere itself was a non-critical mass of plutonium weighing 6.2 kilograms or 14 pounds, about the size of a softball. Remember, it takes almost double that mass of uncompressed plutonium for spontaneous criticality. The Demon Core was scheduled to be used in a 3rd bomb to be dropped on Japan, but became surplus because of Japan's surrender. On August 21st, 1945, Daghlian was trying to slowly approach criticality by surrounding the spherical core with blocks of neutron-reflective tungsten carbide. The more neutrons reflected back into the core, the closer to criticality. Daghlian, alone in the room with only a security guard 3 to 4 meters away, slowly added blocks of tungsten carbide. Unfortunately, he dropped a block on top of the core, bringing it past criticality. A bright blue flash occurred as radiation ionized the air. Daghlian immediately removed the dropped block, stopping the criticality, but it was too late. He died 25 days later from the massive exposure he received. The guard, Private Robert J. Hemmerly, survived the incident and died 33 years later of leukemia, maybe from that exposure, but hard to tell. The Demon Core was then used for another criticality experiment by Louis Slotin. This test was looking for similar data, but had a different configuration. Here, the neutron reflectors were 2 hemispheres of beryllium. You can see the Demon Core in the center. The closer the hemispheres, the closer to criticality. A slight separation was necessary to keep the plutonium from going critical. Slotin was supposed to use shims between the hemispheres to keep them separate. Instead, Slotin decided to hold the beryllium hemispheres apart with a screwdriver acting as a wedge to hold one edge apart. He had done this a dozen times without incident. I think you can probably predict what was about to happen, and on May 21st, 1946, it happened. Yes, the screwdriver slipped. The hemispheres came together, the core went critical, and a flash of blue light from ionized air occurred. Slotin immediately threw the hemispheres apart with his hand, but knew what had happened and what would happen next. He was not the only one in the room. This time there were 8 people in the room with him. Slotin, while obviously not a careful physicist, was a conscientious scientist. He had everyone mark, with chalk on the floor, where they were standing, and created a map. He knew this might supply important data on the effects of the radiation. On this map, you see the people, which I'm marking in red, and the location of radiation monitoring film badges, I'm marking in blue. The demon core I've marked in yellow. This map is labeled with the dosages in Roentgens measured by those badges. Slotin died 9 days later. The next closest person, physicist Alvin Groves, was partially shielded by Slotin, and though he received a large dose, died 19 years later. The rest lived up to 55 years after the incident. Because of the 2 criticality incidents, the demon core became contaminated with fission products and was deemed unusable as a bomb core in future tests. It was eventually melted down in 1946 and recycled for its valuable plutonium. Which brings us, finally, to the subject of nuclear weapons. Plutonium is well suited for this use. Its critical mass is lower than a typical uranium bomb. Remember from the episode about uranium Little Boy, the bomb dropped on Hiroshima? It was a gun-type fission weapon. Inside was a conventional chemical explosive at one end. 2 subcritical pieces of highly enriched uranium-235 were at opposite ends of the bomb, far enough apart to keep them from going critical. When the conventional explosive is detonated, the pressure from the explosion drives the subcritical pieces of uranium together. They now form a critical mass, generating tremendous amounts of energy in a nuclear explosion. The second atomic weapon, Fat Man, was the nuclear weapon detonated over the Japanese city of Nagasaki on November 9, 1945. It works on a completely different principle than Little Boy. Because of the nature of plutonium, a gun-type mechanism would not assemble the more active fissile plutonium quickly enough and keep it in place long enough to allow a significant explosive yield. Physicist Seth Nettermeyer advocated for a device that would use implosion to create a critical mass. The first nuclear bomb exploded in a test called Trinity was a plutonium implosion bomb. Let's look at its internal workings. Remember those jawbreakers you used to enjoy as a kid? They would change colors as you sucked on them. They were made of a series of concentric shells of colored sugar. Well, plutonium implosion devices have much the same structure, but no sugar. The outermost shell is a series of conventional explosives. Part is a fast explosive with an embedded, slower explosive. Together, these made up what's known as a shaped charge. When set off, these are designed to send virtually all the force of the explosion in one direction, inward. The 32 shaped charges surrounded the rest of the spherical assembly in a soccer ball-like arrangement, as you can see in this photo of the charges being test assembled. The next layer inward is the aluminum pusher. It transfers the incoming explosion shock waves. A very thin layer of boron-impregnated plastic absorbs excess neutrons, preventing a pre-detonation of the plutonium. Inside this is a thick, non-fissile layer of plutonium-238 called the tamper. Uranium is very dense. Once this stuff gets pushed inward by the explosive shockwave, its inertia makes it hard to stop, compressing the plutonium-239 core, often called the pit. At the center of all this is a small 20 millimeter 0.8-inch sphere of polonium-210 and beryllium. When this is crushed, it releases a burst of neutrons, initiating the plutonium into rapid fission. When enough neutrons from the fissioning plutonium become available, the uranium tamper also fissions, adding about 30% to the resulting explosion. So first, the conventional explosion of shaped charges compresses the core of the bomb, which then goes critical, releasing a tremendous amount of energy. The first plutonium devices yielded the equivalent to 21 kilotons of TNT, or 88 terajoules for the physicists out there. About 1 kilogram of the 6.2 kilograms of plutonium participated in the fissioning. The rest was scattered into the atmosphere. You can find much more detailed information beyond the scope of this presentation online, an extremely interesting rabbit hole to go down. Assembled, it looks like this museum model and was called the physics package. It fit inside the Fat Man bomb. The rest of the space in the bomb was taken up by batteries, ground sensing radar, and atmospheric pressure sensors used to trigger the explosion at a predetermined height. All this was designed during the wartime Manhattan Project, led by the brilliant physicist J. Robert Oppenheimer. Oppenheimer led a team of extraordinary physicists, engineers, chemists, and almost 130,000 others to develop a nuclear bomb before Hitler's Nazi Germany could do the same. The project had research locations in labs and universities across the United States. On a personal note, I had the pleasure of working with Robert's brother, Frank Oppenheimer. Frank worked with his brother as part of the Manhattan Project. After the war, Frank was blacklisted by the House Un-American Activities Committee to become a cattle rancher in Colorado, of all things, and was not allowed to pursue physics. Frank would eventually create the world-renowned science museum, the Exploratorium, inside the Palace of Fine Arts in San Francisco. Here's an inside view. The Exploratorium has since moved to Pier 15 on the Embarcadero. I worked with Frank up until the time of his death in 1985. This is a very early photo when I still had hair. During those 15 years, many of the Manhattan Project scientists who were Frank's friends spent time with us at the Exploratorium. In particular, physicist and educator Phil Morrison and his wife, artist Phyllis, used to spend every summer with us. Returning to our Manhattan Project subject, Phil carried the plutonium pit of the Trinity bomb from the Los Alamos lab to the Trinity site on his lap in the back of a Dodge sedan. That's over 200 miles. He checked the plutonium pit every hour. Here you see the physicist Herb Lair with the magnesium box containing the plutonium pit. That box was designed by Phil Morrison, who, along with Frank, witnessed that first test of an atomic bomb. It changed them both. These scientists were some of the smartest and deepest thinkers I have ever met. I miss them all. Speaking of the Trinity bomb, it was called the Gadget. We see it here, wired and ready to go, installed in the shot tower. It's not surprising it looks identical to the physics package of the Fat Man bomb we saw a few slides back. In the middle of New Mexico, on the White Sands Proving Ground in the Jornada del Muerto Desert, right here was the place chosen for the test of the first atomic explosion on July 16, 1945. If we zoom in on that site, we'll see that it still exists today. Public tours are given to this site on the first Saturdays of April and October. A 12-foot-high monument was erected on the site, marking the place of the vaporized shot tower. That so-called shot tower looked like this. Here we see the Trinity Gadget being hoisted into place to the top of the shot tower. final assembly, including wiring the detonators for the shaped charges, and the installation of the plutonium pit would take place in the shed at the tower top. I've always found these films a bit horrifying and suspenseful, knowing the potential of that steel sphere. On July 16, 1945, at 11 hours, 29 minutes, and 21 seconds GMT, the world irrevocably changed. The nighttime desert lit up, and a mushroom cloud rose higher and higher, glowing the colors of purple from the air ionized by the radioactive cloud, while the sound of the blast seemingly went on forever, reflecting from the distant mountains. This is an aerial photo of Ground Zero. The blast left a crater 1/2 mile across and 8 feet deep. The desert sand beneath the blast was melted into a slightly radioactive green glass, highly sought after by collectors, called Trinitite. This is a sample owned by Phil, a co-worker of mine. It measures a few centimeters across. Thank you, Phil, for allowing me to photograph it and to measure it with my gamma-ray spectrometer. FYI, it's not highly radioactive anymore. I have a few samples of my own. I don't remember where I got this piece. It's the smallest of the 3 samples I own, only a few millimeters across, in a nice display box. Magnified, you can see its typical greenish colors. The second piece was sent to me by my friend, Jerry, who purchased it at the National Atomic Testing Museum in Las Vegas. They no longer sell Trinitite. The last I obtained from Atomic Ed at the Black Hole. Let's check this one out with the Geiger counter. Here I have my piece of Trinitite from the Black Hole, and on my Geiger counter, let me turn it on. As I bring it close by, listen to the clicks. Trinitite is only mildly radioactive, so it's really not a hazard to humans. Let's get back to our slideshow. Again, you can see here in the photo the typical greenish color of Trinitite. The Black Hole was a surplus store and museum all-in-one in Los Alamos, New Mexico. Here you see friends and co-workers, Karen and Mike, standing with Ed, and with me and Tim Hunkin both kneeling in front. You may know Tim from his fantastic TV series, The Secret Life of Machines. Ed worked in Los Alamos after the Manhattan Project, perfecting the plutonium implosion devices, making them more efficient, smaller, and more destructive than the first 2 gadgets. He regretted his work and became a dedicated pacifist for the rest of his life. He founded the Omega Peace Institute. Note, they have a critical mass every Sunday. Plutonium serves no known biological purpose, and you hopefully have none of this stuff inside you. If you do, the Department of Energy wants to know about it. Aside from its radioactivity, it's a toxic heavy metal, similar in its effects to lead or mercury. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about plutonium. Manhattan Project. Climbing the tree of knowledge for forbidden fruit. In the next program in this series, I'll examine the element americium. You almost certainly do have some of this radioactive element in your home. I hope you'll join me and find out where. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element plutonium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And of course, I'm required by law to say this, smash that subscribe button.